So in this question, we're asked to figure out something and write a paragraph response. And so what we want to do is tease out the important elements and do the work necessary to create the bullets for our essay. So we've got two stones, mass M and 2M. Each are launched straight up by a cannon. The less massive stone has twice the speed of the more massive stone. Which one attains a higher maximum height, and how many times higher does it go? So the first thing we want to note here is we've got M and 2M. And so the first thing we really need to know is that the mass has no effect. Gravity acts on them, all objects equally. And that equal action is G, which is about 10 meters per second squared. So it doesn't matter that you got M and 2M. So that's the first thing we're going to need to say there somehow. So we've got them launched straight up by a cannon from cannon. So there's one cannon and there's a mass, and the other cannon, which is 2M. The less massive stone has twice the speed, so it gets launched with, say, 2v0. And the second one then has v0. So if the small mass is m, the large mass is 2m, and the small speed is v0, and the twice the speed is 2v0. So you want to know which one reaches a greater maximum height. Well, what I have taught you is to always try to solve every problem using the average velocity formula. So let's do that and see what we get. So the average velocity is delta z over delta t. So we want to know which one has the maximum height. That's going to be delta z. So rearranging delta z, we get delta z equals v bar delta t. So ultimately what we want to know then from these two situations is how do the times compare and how do the average velocities compare. So let's first, we'll just start with we can start with either one. Let's do the average velocity. Well, what we know about each of them is they're going to start off with some initial velocity, and at the top, maximum height, the velocity is going to equal 0. Well, our relationship for this is v equals at plus v0. And at the top, the instantaneous velocity will be 0. The acceleration is g, and there's some time, and we'll say that's the time of the time of m, or we just call it the time of the small one, or time of m. And the initial velocity is 2v0. So if we're trying to find the time, we can solve for the time, and we get gtm, the acceleration caused by gravity, times the time of the mass is minus 2v0. And therefore, the time of the mass is minus 2v0 over g. So that's an expression for the time of the mass, for the smaller one with m as a mass. Now let's take a look at the larger one. So v equals at plus v0. At the top, it will also have a velocity of 0. It will experience the same g, and the time in this case, we don't know it's going to be the same, so it's going to be time of the 2m. And the initial velocity is v. So by the same token, we have gt of the 2m equals negative v0. So the time of the 2m is minus v0 over g. So what we can see in comparing these is that the time of the smaller one is going to be twice that of the other. So if we've got delta z of v bar delta t, well, delta t we know is now twice. It's the equivalent of twice the other. It's twice the size of the other one. So we put this 2 in here for this guy. And for the green one, the larger one, delta z 2m, we got v bar delta t. And the delta t in this case is v0 over g, and so that's 1. So immediately we know that the height is going to be at least twice as great. Now we need this average velocity. Well, we know there's a starting velocity and a final velocity. And so that average velocity, we can use the second average velocity formula, which is v bar equals v plus v0 over 2. Well, the final velocity is 0 at the top, and the initial velocity is 2v0. So we're left with an average velocity of the red one of v0. Now, the larger one, we have an average velocity, which is v plus v0 over 2. Velocity 0 at the top, plus v0 to start, and 2. So we have v bar is v0 over 2. So what we see then is that the time for the smaller massed object is twice as large as the other one. So not only is the time twice as large, the velocity, average velocity, is twice as large. So we've got an average velocity equivalent to 2, a delta t of 2, so that's going to give us a relative value of 4. And the larger one, for the 2m, the average velocity is 1/2 as much, or we put in a 1 in this case, to keep it whole, we're left with 1. So the delta z of the smaller one should be 4 times as large as the other one. Now we can test this out. We can actually put in some numbers here to see, for example, to test it. So we did this as pure function, but we could do this by saying, like, let's say over here that the initial velocity is 20 meters per second, and for the heavy one, the initial velocity is 10 meters per second. So the velocity of the larger one is half that of the first one. Well, we can solve this. If we take a look at the smaller mass one, well, how long is it going to take to get to the top? V equals at plus v0. Acceleration is minus 10, and we've got a v0 of 20. So we've got 10t equals 20, so t equals 2 seconds. And for the large mass equals negative 10t plus 10, so 10t equals 10, and t then equals 1 second. So we can see we were correct. The time of the smaller one is twice that of the larger one. And then when we do the average velocities, well, we've got v bar equals v plus v0 over 2. That final velocity at the top is 0 plus 20 over 2. And so that gives us an average velocity of 10. And for the more massive, v plus v0 over 2, 0 plus 10 over 2, which is 5. So we can also see that the average velocity is twice as much as the other one. So again, we've reinforced it both as a function and by numbers. So it's now we need to go through all of this work we've done. We've figured out the answers, and in this we have the work of our important bullets. So we've already identified that this needs to be an important bullet. The first one, the mass has no effect. That's a distractor. The second thing is we can say, in terms of our thought process, that this vertical distance is related to the average velocity times the time. And because the instantaneous, so then we can go to the time, breaking down the time, because the initial velocity is twice as large, it will take twice as long for it to reach the top. And that's what we saw over here. Similarly, since the average velocity is the average of the initial and final velocities, it's going to be 1/2 the initial velocity. Well, since the initial velocity of the smaller one is twice as large as the first one, the average velocity will also be twice as large. So twice the time and twice the average velocity equals 4 times the displacement. And so those are the bullets and the trains of thought that we want to have. And then there's that art and craft of writing that as succinctly as possible.